So activity number 2 begins with the vector field f of x and y is yi minus xj. So its components are y comma minus x. And when we visualize the field itself, it has this shape that we see over here. And so when you sort of squint at this vector field, it kind of looks like the picture of something that's circulating, right? Something that is kind of, circulating about the origin. And that if I were to drop a boat into this current here, that the boat would just sort of float around this way in circles around the origin. Right? And so this activity is about kind of making that idea precise and kind of thinking about how we might justify why the integral curves of this vector field, right, the parameterized curves that just follow the vector field arrows, that those curves are going to be circles that are traversed in a clockwise fashion centered at the origin. And so the first step is going to be to just visualize, plot some integral curves, and we'll use Matthias Kauski's Vector Field Analyzer 2 tool to do that visualization for us, both for precision and also so that we don't have to get out a piece of paper and then snapshot it and upload it and all that stuff that's hard to do when you're teaching an online class. So that's where we'll start, is just to visualize a few integral curves. And again, you can, when you use the differential equations in Flows menu and click integral curves, you can put in just one point and then click stop and go to trace out the integral curve. You can also put a bunch of points if you want to, sort of however you like to do it. In fact, I believe it also gives us the ability to click and drag to draw an entire sort of line's worth of starting points and then watch where they all go. And so whichever way you'd like to do it as part of this exercise, you're welcome to do. So that'll actually get you parts A and B both simultaneously. And then parts D through F, and I've actually added a couple more parts, G and H, to the version that we're going to work on, actually sort of get us into the, okay, why should we expect that the integral curves for this particular vector field have the shape that they ultimately have? So those are going to involve just a little bit of algebra and vector geometry, I think, to verify why it is that things work the way that they appear to work. So A and B as visuals, and then D, E, and F as vector geometry exercises. So let's start with A, B, and C, and then we'll take a pause, debrief, and then go on to D, E, and F after that. So using the integral curves of a vector field is a really good way to get a sense of what the overall shape of the vector field is, just by looking at which curves actually follow the arrows that the vector field specifies, which curves have velocity vectors exactly equal to the vector field vectors at every point along the curve. So for this vector field, yi minus xj, we plot some integral curves, and we find out that, depending on where we choose our initial point for these curves, we get either a circle that looks like this, or possibly a smaller circle, possibly a bigger circle. All those circles are centered at the origin. And so, true to form, right, if we were to just place a boat inside of this vector field, it would travel along a circle in a clockwise fashion, and that circle would be centered at the origin. So that's for this particular vector field. Obviously, every different vector field is going to have potentially different shapes to its integral curves. But in this way, we can kind of think of vector fields as one other source of where we can get parameterized curves from, right? That chapter 9 topic that we first met early in the semester, right? We can get a parameterized curve by taking a vector field and asking, what are the integral curves of this vector field? What parameterized curves follow the arrows of the vector field? And so we're just going to do a couple of vector geometry exercises to wrap this activity up. First of all, verifying that f of x and y, so the vector field output in this example, is orthogonal to the vector x comma y. In other words, a vector that's has its initial point at the origin and has its terminal point at the point x, y. So verify that those are orthogonal to one another. And then also talk about what is the relationship between the function f of xy equals x squared plus y squared and the vector xi plus yj. And then what, if anything, does this tell us about the relationship between this vector field and circles centered at the origin? So we're going to do a little bit of vector geometry and calculus to wrap up this activity in parts D, E, and F. So in part E, in part D, you verified that the vector field, capital F, is orthogonal to xy. In other words, if we were to draw a vector from the origin out to any point in the xy plane, then the vector field vector that we get at that point points perpendicularly to that vector that starts at the origin and ends at xy. And so in particular, what that means is that if I have an integral curve, which is going to be tangent to, it's going to follow the arrows of the vector field, then the tangent vectors to that integral curve are always going to be perpendicular to that line that connects my point to the origin. And what that tells me, therefore, is that if that line connecting me to the origin is the radius of a circle, then the tangent vector to my integral curve is going to be perpendicular to the radius. And that is a fact from ye olde geometry, right, which is that the tangent line to a circle is always perpendicular to a radius of that circle drawn to that point. Right? So that's sort of the first clue that we're going to have integral curves that are circles, is that the line joining each point to the center of my circle is perpendicular to the vector field vector that gives me the velocity of that integral curve at that point. But then the next sort of step to reinforce that point is they ask, what's the relationship between, so this part E is almost completely decontextualized, right? It doesn't have anything to do yet with the rest of this problem. And you correctly identify that the relationship between the function f of xy equals x squared plus y squared and the vector xi plus yj is that the gradient of this function is a positive scalar multiple of this vector, right? It's c, and in this case, what's the value of c? I think it's 2, right? It's 2 times the vector xy. And so the gradient of f, the gradient of this little f function, points in the same direction as the vector x comma y. But that vector x comma y is the vector that starts at the origin and takes me out to a point xy in the xy plane. So what we've found is we've found a function, little f of xy equals x squared plus y squared, such that the gradient points in the same direction as the vector xy, but the vector xy is perpendicular to the vector field at that point. So we found a function whose gradient is perpendicular to this vector field. So if we were to plot both this vector field and also the gradient vector field of x squared plus y squared, we would get a bunch of little right angles, like pairs of vectors that are perpendicular to one another at every point that we see. And so the question that we're asking in F here is, what does the result of part E tell us about the relationship between our vector field and the circles centered at the origin? You correctly identify that the magnitude of our vector field actually is equal to the radius of the circle that contains its integral curve. But this first question, what does part E tell us about the relationship between the vector field and these circles, is the even more interesting part. This is the part that's going to anticipate the work that we do next on gradient vector fields in activities 3 and 4. All right, so to wrap up this set of observations and to kind of leapfrog us into the discussion we're about to have next, we figured out that the gradient of this function x squared plus y squared, right, which sort of came out of nowhere in this problem, but the gradient of this function happens to be parallel to the vector xi plus yj, and meanwhile our vector field was perpendicular to the vector xi plus yj. So what does this have to say? It tells us that because the gradient of f is orthogonal, the gradient of the little f is orthogonal to the vector field, and it's parallel to xy, which is the gradient of f is parallel to that xy, it means that the vector field is going to point in a direction that keeps the value of x squared plus y squared constant. And that's why the integral curve ends up being a circle. So here's my sort of graphical summary of what you just did. Hopefully this will help to clarify the couple of sentences that you wrote there. So we have a vector field, f of x and y, right, which at every point is perpendicular to the vector xy, which starts at the origin and goes out to the point where we draw this vector field arrow, right, the initial point. And also that the gradient of the x squared plus y squared function is likewise parallel to this purple vector down here, right? It's parallel, and therefore that gradient is perpendicular to our vector field. And so what that tells us is that in the direction of the vector field itself, so as long as we're always following the direction of my vector field, it's going to be the case that the directional derivative of this function, f of xy equals x squared plus y squared, because the directional derivative is the dot product between the gradient of f and the direction in which we're moving, and those directions are perpendicular to one another at all times, is what you told me correctly, therefore that directional derivative is always 0. And so in the direction that we are moving along the vector field, the directional derivative of this function f of x and y is 0. And so this function is not going to change. Its rate of change in the direction of the integral curves of our vector field is just 0 at all points. And so along the integral curves of f of x and y, this function has a constant value. So the integral curves reside within sets of points in the xy plane that have a constant value of x squared plus y squared. But those points in the xy plane that have a constant value of x squared plus y squared are exactly the circles with the radius at the origin, whose radius is the square root of whatever that constant is, right? X squared plus y squared equals r squared. So this is a way for us to figure out what shapes the integral curves of this vector field had without having to solve a differential equation, which also gives us the sort of time dependence of the integral curves. If we don't care about that, if we just care about the shapes, this is one way to find the shapes. It doesn't always work. And we had to kind of pull out this x squared plus y squared function and miraculously observe that its gradient was perpendicular to the vector field that we were working with. But in that special circumstance, where I can find a function whose gradient is perpendicular to my vector field, then we're going to know that the integral curves of my vector field reside exactly along level sets, contours of that function, little f. And the contours of this particular function, little f, are exactly the circles with their center at the origin.